So we have new notation of Laplacian, and the previously L was the d minus a, right? In the 2 slides before. And when we use the linear algebra, so it could be formulated like this. So our goal is to minimize the cut, right? We try to identify the best S, which minimizes the QS, the graph cut function. And we also give another balanced cut constraint. So make it balanced cut. The summation should be the 0, right? Or was +1 and -1. When number of the +1 and number of the -1s are the same, and it will give the 0 value. So this is the integer minimization problem, and exact solution is NP-hard. So the optimization, we give the objective function and the constraint, and we learn the optimization solver, right? But this is the NP-hard problem. And with that reason, we make it the problem to the continuous problem. A discrete problem. So previously, we are able to find the S, right? The S should be the composed of the integer values, and which satisfies these conditions. We try to relax the problem, make the problem to the continuous problem. So now we are able to get the flat value for the S. We introduce new notation. X is the flat value. So instead of this, so we give this constraint. So now we're able to get the flat, and we still get it this. So once we find the best X, and to recover the S, because we need to get the partition eventually, so we just run them up, even though, say for example, it's minus 0.5 and 0.5, so we assume that we get this flat vector. We just considering their sign, and we can recover +1 and -1, something like that, right? Or in this case, -1 and +1. So exact constraint satisfies the Dirac equation, but not other way around. So this could be formulated constraint optimization problem using Lagrange multiplier. So we have this constraint, so it could be defined in this Lagrange multiplier, right? This one. We have this, and this is actually exactly the same as the solving the eigenvalue and eigenvector problem. The formulation itself is. So we get so this shows the eigenvector eigenvalue problem. So x becomes eigenvector and lambda becomes eigenvalue. So the researcher found that, so we're not going to talk about the detail, but the first smallest eigenvector, which means, so we have several eigenvalues, right? Multiple eigenvalues. And when we sort by considering the magnitude, so we are able to find the smallest eigenvalue, and we get the corresponding eigenvector. And the eigenvalue is always, the smallest eigenvalue is always the 0 from the Laplacian. So for the spectral method, so in this case, so we use the eigenvalue and eigenvector. Now this problem is converted to the eigenvector and eigenvalue problem. That's why we call this is a spectral method. And we look for the second smallest eigenvalue and eigenvector in this eigenvalue problem. And as long as we are able to find smallest eigenvalue and each corresponding eigenvector, we are able to find the partitions. So, in summary, the minimizing graph cut problem is relaxed in the flat, considering the new flat identifier. Solving the optimization problem is the same as solving the eigenvalue eigenvector problem, and in practice, and people actually prove that, and second eigenvalue and eigenvector is able to find the identifiers. So that is the key. And to get the eigenvalue and eigenvector, we use the Rayleigh-Ritchie quotient. So we minimize this. So it is just related to the eigenvalue eigenvector problem. So I'm not going to talk about this much. So this is the summarization about the spectral graph partitioning. So we get this input. So we expect this output. So to get the output, we compute the Laplacian matrix. And we get the second smallest eigenvector. And considering its sign, so x2 is second smallest eigenvector, we get the indicator vector, which means now we have the two partitions. So simple, right? So its underlying theory is a bit hard to follow up, but the output-wise, very simple to follow. That's why the Laplacian matrix is important in the graph domain, and it is related to the partitioning and many useful properties it have. So you may wonder, the graph cut, the mean cut, the minimizing the graphic cut is, it sounds ridiculous. So minimizing the graph cut is always satisfactory. Here we have the example. So in this case, minimizing cut is this one, right? When we define the partitions, something like this and this, because the minimum cut is just one, because it has one edge between the two partitions. But to us, it looks not optimal. So to us, considering the ground truth in here, the optimal cut is found in this direction. So the minimizing the graph cut, so the objective function, and the way it considers external cluster connections only. So it does not consider internal cluster densities, and it is likely to find these like some outliers the more, and we don't think this is the optimal partitions. So now we have the optimization criterion once again. So we have several alternatives, some normalized version, and this. So we see actually there are better the criterions or not. And obviously the graph cut is not good. So you may compare the ratio and normalized cut and their properties. And from this input graph data, so the partitioning, the first partitioning is this. So we use the red color, and another second candidates. So we're considering two different partitioning the research. So we respect this one. So we don't think this is good, but the graph cut wise, this is the best partitioning. So ratio cut, we computed the ratio cut. So I haven't put all the details. The result wise ratio cut is 0.56. Normalized cut is 0.52. What about this one? So we expect we observing that this is the optimal the partitioning the cut. In this case, the ratio cut, we have the smaller value. Normalized cut is also getting smaller value than in this case. So both of the cuts prefer the balanced partition. So we think this is more appropriate, right? So how do we get the partition with the normalized cut? So let me give you the result wise, we just compute the normalized Laplacian. So full derivation is, you can find the full derivation in this tutorial. We compute the normalized Laplacian like this. You understand what the D means and A, right? Degree matrix and A's adjacency. And we get the second smallest eigenvector once again, and considering the sign, and we get the partitions. So output-wise, still looks very simple, right? So we can, so here, let me leave the objective function. So using the linear algebra, so the two cases, ratio cut and normalized cut, we minimize this one, and in the case of the normalized cut, we minimize this one. But still, the optimization process is the same as the eigenvector solving problem, but objective function is they are different from the graph cut based the optimization, the objective function of that. So summary, so we have three basic stages: pre-processing. So from the input, we need to construct the matrix representation. We need to have the adjacency and degree matrix and Laplacian matrix. We get the eigenvalue eigenvectors, and we need to map the point. And here we focus on just one eigenvector, right? And considering the sign, we get the clusters. Here we saying like more eigenvectors and more clusters. So to get the more clusters, we need to consider more complicated settings, and we'll introduce the following slides. So another visuals about the procedure. So we need to build Laplacian from the graph. We need to decompose to find the eigenvalue and eigenvector, and map vertices to the corresponding components of the lambda 2, and we get the cluster by looking at the sign, right? So in practice, we can consider this sign, and more expensive approaches, we attempt to minimize normalized cut in the dimension. So we sweep over the ordering of nodes, the eigenvectors, and we find the optimal partitions. Right. So this is the example. So we have the graph input, and just looking at second largest eigenvectors, and these are the node IDs we already ordered by looking at the value. So now we see we find two clusters mapped onto this one and this one. And when we have more complicated graph, so we able to find these. The inside of the negative eigenvalue and positive eigenvalue, so we are able to find the partitions, something like this. What about the other eigenvectors? So we have talked about the second smallest eigenvectors, and we have the third smallest eigenvector, but still we're observing some partitions, something like this. So when the graph is the noisy, and we expect some interesting research. So from that observation, so we'll give you a lot of details about it. This is the input adjacency matrix. So the result of the spectral clustering, and this is the result. We just reordered based on the partition ID, and we are able to find some beautiful block diagrams here. So we have K-way spectral clustering. So it is related. So it is to get K different clusters, T different partitions. So we have two basic approaches. So now we have the signs plus and minus. We were able to find two partitions, and then from this partitions, we learn the spectral clustering. You're able to get the two partitions once again. In this case, we have three partitions as output, and we may run the spectral clustering on this partitions, and we get two. So with this way, we get the K number of the clusters. Otherwise, we're just looking at the eigenvectors, and we just learn the k-means, and we can get the K number of clusters. So from my observation, for example, at the second smallest eigenvector, and we get these partitions. So when we just use the sign, we're not able to find the four clusters. But in this case, this is a one-dimensional data though. So when we use the k-means, the centroid will be placed in here, likely to be placed here, right? So when we learn the k-mean in this one-dimensional data, the vector, we get these. So we can utilize multiple eigenvectors. So even third smallest eigenvectors in the fourth and fifth, and sometimes it's useful to understand the complicated graph data. So using the multiple eigenvectors, and we'll run the k-means. And in practice, it returned better segmentation and clusterings. So these indicating the recursive partitioning. So this shows this one. So we keep running the two-way spectral clustering. Yeah, first we get this, and from this one came to here, and we get partitions, and this one, then this. From this, we get partitions, this one and this. And this indicates the way to use the multiple eigenvectors, and similarly we get the matrix representation. And different from the regular spectral clustering, we get the multiple eigenvalue and eigenvectors, and we get the row dimension representation considering k number of eigenvectors, not the second smallest eigenvectors. And we run the k-means on the representation, and we get the k clusters. So this approach is used in the image segmentation domain. So the output is something like this. It looks promising, right? So each one shows the result from the each eigenvector. So we consider all the stuff, and we are able to find the better segments in the input image. And compared to the spectral clustering, using the multiple eigenvectors, this is the pixel-wise k-mean. So because when we're considering the pixels, the RGB value, so it has some similar stuffs in here, right? It's in gray and gray in here, some of the ear around. So we have some weird result, but we're considering the multiple eigenvectors, we get the better segments. All right, so we have multiple references, and these are very kind tutorial about the spectral clustering. So you are able to follow up all the derivation procedures, and so the segmentation, the paper is published in this paper, the PARMI journal, and the many useful articles are listed up. And thank you for your attention. And if you have any questions, let me know, and have a great the rest of the days in this week. Bye bye.